Yeah, hello everyone. Let's start today's class. So continue from yesterday. Today we'll talk about section 8.2 for this orthogonal diagonalization. Let's first start with the definition. Yep. Okay, so it says if A and B are two square matrices, then we say that A and B are orthogonally similar if there exists a orthogonal matrix P for which like P transpose times A times P is equal to B. Yeah. So if you still remember, like before we talk about this A is similar to B if there exists an invertible matrix P, if you want to find out, it's in the definition of like 4.2.4, it says if P is only invertible, then we can say A and B are similar if the P inverse times A times P equal to B. We will say A and B are similar. But now, that's in chapter 6. But today we have a bit more requirement for P. Let's say if P is not only invertible but also orthogonal, as we said yesterday. So now we can, and they satisfy this. So now we say A is orthogonally similar to B. Yeah. So of course, yeah, from here, for example, if we know this, of course, we can write what is A. We can write A in terms of B, right? Because, so it is easy. So we put the P, B, P transpose, and we use the fact that P times P transpose is the identity matrix because P is orthogonal. Yep. Okay, and if A is orthogonally similar to a diagonal matrix D, if B is diagonal, this matrix D is diagonal, then we say that A is orthogonally diagonalizable, and that this orthogonal matrix P orthogonally diagonalizes A. Okay, it's just the definition. Yeah. So now if A can be orthogonally diagonalized by orthogonal matrix P, then we can write A like that. Oh, sorry, yeah. If A is orthogonally diagonalized, we can write A like that, right? Yeah, just from here, can write A like that. So now we can express A in terms of a diagonal matrix D to orthogonal matrix P and P transpose. Okay. Yeah, the reason we do that is because for P and P transpose and D, they are very nice matrices. So we can, yeah, and this will be very useful in many calculations. So now we can ask, since these orthogonal matrices have such nice properties as we discussed yesterday, so it is natural to ask which matrices can be orthogonally diagonalized. Yeah. So what kind of A can be, the matrix A can be orthogonally diagonalized? So here is the theorem. It says if A is a n by n matrix, then the following statements are equivalent. Item A says A is orthogonally diagonalizable, and B is A has an orthonormal set of n eigenvectors, and C A is symmetric. So we know for symmetric matrix, it is orthogonally diagonalizable. And also, if A has an orthonormal set of eigenvectors, it is also orthogonally diagonalizable. Yeah. Let's try to prove from A to B. Let's try to prove this. Okay. So if you still remember, like basically, I guess in algorithm, there's an algorithm called 6.26 in chapter 6. So we know if matrix A is diagonalizable, just diagonalizable, then we know how to diagonalize A. If A is diagonalizable, then we know we can find an invertible matrix P and a diagonal matrix D such that we can write A equal to P times D times P inverse. And how we do that, that is in this algorithm in chapter 6. Yeah, and also in that algorithm, how do we find this P and D? So how do we find the P? Actually, the column vectors of P, okay, they are eigenvectors of A. Eigenvectors of A. Yeah, okay. So we find all eigenvectors of A, then we put them as a column vectors, then we get this P. And this P can diagonalize A. Yeah. But if now P is not only invertible, here we say if A is orthogonally diagonalizable, this means P is orthogonal, right? If P is orthogonal, then we know from the theorem 8.1.4, it says if P is orthogonal, then these column vectors form an orthonormal basis. So it's a column vectors of P form orthonormal basis. Okay, so if we combine these two, then we know the eigenvectors of A form orthonormal set. Okay, yeah. So we know if A is diagonalizable, we know this P, the column vectors of P are eigenvectors of A. But now we know P is orthogonal. Then we know the column vectors of P form an orthonormal set, which means the set of eigenvectors of A form an orthonormal set. Okay, the proof is quite simple. That's from A to B, and then from A to C, or B to A, or let's say B to A. This will be in the problem set, and from C to A, yeah, that will be in the MTH 2025 workshop. Okay, so we will not talk about this here. Yep. Yeah. Yeah, but part C, so we don't prove it here, but we will use this later today. They say A is symmetric. If A is symmetric, A is orthogonally diagonalizable. If A is orthogonally diagonalizable, then A is also a symmetric. It's a symmetric. Yeah. That's this theorem. Okay, then let's prove another one. It says if A is a symmetric matrix, then eigenvectors from distinct eigenvalues are orthogonal. Okay, so let's try to prove this. So let's A is a symmetric matrix because we want to show the eigenvectors from two distinct eigenvalues. So let's let, for example, Vi is the eigenvector of A with eigenvalue lambda I. Okay. And Vj to be a vector, eigenvector of A with eigenvalue lambda j. Yeah. So now we want to show Vi and Vj. If lambda I not equal to lambda j, we want to show Vi and Vj, these two eigenvectors, are orthogonal. Let's try to show that. So let's start with this. Dot product A Vj. Okay. So oh no, sorry. Let's do this. So the dot product of these two vectors, the first vector is A times Vi, the second vector is Vj. Of course, we know, put it here, we know this is just equal to lambda I times Vi dot product Vj. Right. So let's continue from here. Yeah. So we know that this is just equal to that. So then we can write, this is dot product between two vectors. If we write this in terms of matrix multiplication, that would be AVI. This is a vector, but we need to transpose it. This is another vector. So now this is for matrix multiplication, right? Because we just put the column vector to a row vector by using its transpose. So then what's this? Then because the transpose of the product of two matrices is equal to the product of their transpose. So we have that, right? And then, yeah. And then we need to use A is symmetric. Before we have to use A is symmetric. Now, because A is symmetric, so A transpose just equal to A. Right? Yeah. And then what is A times Vj? A times Vj is just lambda j Vj, right? Because Vj is the eigenvector of A with eigenvalue lambda j. So lambda j is just a constant we take in front, just a number we take in front. So what's left is Vi transpose Vj. Yeah, and of course this is just, if we can write this as like a dot product or something. So this is Vi dot product Vj. Okay. Yeah. So then now we can compare the right hand side to the very left hand side to the very right hand side. So if this is true, this means that lambda I minus lambda j square times the Vi Vj is dot product of them equal to 0. Right? Yeah. But we know, because we assume these two eigenvalues are not equal. So these two eigenvectors, they have to be orthogonal. The dot product is 0. Yeah, okay, yeah, the proof of this is quite straightforward. Yeah. Any question to this? Okay, if no, let's continue. Yeah. Yeah. So the theorem we just proved here, 8.2.3, and another theorem 7.3.11, 7.3 in chapter 7. It just say any non-zero finite dimensional inner product has orthonormal basis. So yeah, so this implies that we have the following algorithm for orthogonally diagonalizing a symmetric matrix. Okay, so now this is the algorithm to orthogonally diagonalize symmetric matrix. So it's similar to the algorithm in chapter 6, where we use that algorithm to diagonalize a matrix. Yeah, here is orthogonally diagonalize that. It's matrix A. Let's say if A is a symmetric matrix, then we first what we need to do is that we find a basis for each eigenspace of A. So first we find all the find the eigenvalues, eigenvectors, and we can then find the eigenspace corresponding to each eigenvalue. Yeah, and for in each of these eigenspace, we can find a basis. We can find the basis for that eigenspace. But these bases may not be orthonormal. But we can use this called Gram-Schmidt process to convert this given basis into an orthonormal basis. So the basis we find in the first step may not be orthonormal, but we can always use this process to make it orthonormal. Yeah, you can refer to it, that place to see more details. And once we find the orthonormal basis, then we can we can form this matrix P. Now this column vector of this matrix P are just the union of all the basis vectors found in the step 2. Okay. Yeah. So then when we find this P, so we will make sure. So we will know this P is a orthogonal matrix, and this P will orthogonally diagonalize matrix A. And the eigenvalues on the diagonals of D will be in the same order as their corresponding eigenvectors in P. Just how we because we have these eigenvectors from A, then we make them we have this basis from A, then we can construct a P, but by letting this basis to be the column vectors. Then which basis is the first column, which one is the second column? That will be, once you fix this order, then the eigenvalues in this diagonal matrix D will follow the same order. Let me give you an example of this. So, for example, suppose it's A matrix A, with a symmetric matrix A. For example, has only let's say 3 distinct eigenvalues. Let's say lambda 1, lambda 2, lambda 3. Yeah. And the dimension of the corresponding eigenspace for each of them may not be 1. Their dimension can be anything. For example, for example, we let E lambda I to be the eigenspace corresponding to the eigenvalue lambda I. Okay, so of course we know the eigenspace, they are orthogonal. If I not equal I not j, different eigenvalue, their eigenspace are orthogonal. Yeah. So so if let's say if we find, by using this algorithm, we find the basis, orthonormal basis for each eigenspace. For each eigenspace is E lambda 1, E lambda 2, E lambda 3, and I just call them, for example, V1, V2, up to VK1. These K1 vectors, they are the basis of, they are the orthonormal basis for E lambda 1. And then W1, W2, up to WK2, they are the basis for E lambda 2. And I can use U1, U2, up to UK3. They are the basis corresponding to EK3. You just each of them is a column vector. You just list them here. You get P. You get a square matrix P. So of course, it's K1 plus K2 plus 3 K3 is just equal to the n, where A is a n times n matrix, symmetric matrix. Okay. So K1 plus K2 K3. Then how do we write down D? Just say the D is a diagonal matrix, and the diagonal entry is just the eigenvalues of A. But then we have to order them, like it's always lambda 1, lambda 1, lambda 1, up to lambda 1. Then, so this is the first K1 columns or rows, a bit diagonal, yeah. And then then it's K lambda 2, then it's lambda 3, yeah. And let's say how many columns here is K1, how many columns here is K2, how many columns here is K3. Yeah, because we will write down our P like from in that order, so we just write down this D following that order. Yeah. Okay, this is just a vague, like a general, not vague, but general example. But now let's consider a more explicit example. Find the orthogonal matrix P that diagonalizes this symmetric matrix A. Now this A is very explicit and very simple, just 2 by 2 matrix. So we just follow that algorithm. So we find basis for each eigenspace of A, but to do that we need to find the eigenvectors and eigenvalues. So the first, because you can note, we know that A is symmetric, right? So which means, okay, A can be, from the theorem, A can be orthogonally diagonalizable. Diagonalized. Okay? Then to do that, we first find the eigenvalue and eigenvectors of A. So how to find eigenvalues? So we just study the characteristic function, is which the determinant of is lambda I minus A. Yeah, right. Yeah. So this is just equal. This is very easy. It's a determinant of lambda minus 3, lambda here. Sorry, just minus 1. Yeah. And what's the determinant of this matrix? That's just easy. Just this minus 1. So this can be factorized as lambda minus 4, lambda minus 2. Yeah. So from here we can read the eigenvalues. So the two eigenvalues, the first is 2, the second one is 4. Right. I'm pretty sure everyone know how to find the eigenvectors corresponding to these two eigenvalues. Yeah. So I just write down. So for this eigenvalue lambda 1 equal to 2, you can easily find the eigenvalues is just 1, 1, 1, negative 1. Yeah. And corresponding to lambda 2, the eigenvector is just 1, 1. Okay, so now we, this example is simple. So the eigenspace, so we find a basis for each eigenspace. But it is not orthonormal because they are not unit vectors. In each eigenspace, there's only one vector. But now if we want the orthonormal basis, we need to make them to unit vectors. So let's say to get a orthonormal basis, so we just define, let's say W1, it's a V1 divided by the norm of V1, which is 1 on root 2, 1 minus 1, and W2 is V2 divided by the norm of V2, which is 1 on root 2, 1, 1. Okay, now we get an orthonormal basis for each eigenspace. Then we can write down P. P is just W1, W2. The column vectors are just W1, W2, which is equal to 1 root 2, 1, negative 1, 1, 1. And what is D? D is a diagonal matrix, and the diagonal entry just lambda 1, 2, lambda 2, 4. The other 2 is 0. So you can double check if you have P and D like that, you can write down your A, it's a PT, D, P. So, sorry, the other way. So now you can this P orthogonal, or you can double check P is orthogonal, and then this P A can be written as P and D like that. So P orthogonally diagonalized A. Yeah. Question for this example? Yeah, it's a very easy example to show how to orthogonally diagonalize a symmetric matrix. Okay, yeah, that's for section 8.2. Yeah. So yeah, then let's move to section 8.3. Singular value decomposition. Singular value decomposition, yeah. Yeah. So before we define what is a singular value decomposition, let's start with the following theorem. Yeah. It says A. Now A is not a it don't have to be a square matrix. It's M by N. Matrix. Then this theorem says the A transpose times A is orthogonally diagonalizable, and the B is the eigenvalues of A transpose times A are non-negative. Okay, let's try to prove this too. So the first part is very easy because how to show this A transpose A is orthogonally diagonalizable? From the first theorem we talk about today, we just need to show A transpose A is symmetric, right? And it is indeed symmetric because if we take the transpose, we will have the transpose, we will have this is equal to that, which is exchange the order. we put the transpose inside and we extend them order, then this is equal to A transpose times A. Okay, so indeed, A transpose A is symmetric, and yeah, then A times A is orthogonally diagonalizable. Okay. Then part B. The eigenvalues of these are non-negative. So just say if a matrix is orthogonally diagonalizable, then its eigenvalues are non-negative. Okay, and let's try to prove this. Yeah. So prove this. Let's prove this. Let's first, because we know A transpose times A can be orthogonally diagonalizable, and so we can let V1, V2 is vectors, Vn, so be orthonormal basic eigenvectors of this, and with eigenvalues lambda 1, lambda 2, lambda n. Yeah, this is also the first part B of the first theorem we talk about today. Just say if this matrix is can be orthogonally diagonalizable, then its eigenvectors form orthonormal set. Okay, so then let's consider this. This is V1, V2. They are not the eigenvectors for A, but the eigenvectors for A transpose times A. Okay, so then let's consider this: A times Vi dot product A times Vi. Okay, so we know this is the norm of A times Vi to a power of 2. So which means this is this must be non-negative. We know this, right? And then let's continue from here. So we can write these as, we can make the column vector to a row vector. We just get rid of the dot product. We use this matrix multiplication. So then we just apply the transpose to A and the Vi. So we will get Vi transpose A transpose A Vi. Okay. And then Vi is the eigenvector of ATA with eigenvalue lambda I. So we can, so for this part, we can is equal to that. And of course, we have Vi transpose in front. Yeah. Then again, what's this? This is equal to lambda I, the Vi dot product Vi. There's a dot here, dot product Vi. Okay, of course, the Vi dot product Vi is just the norm of Vi square, which is 1, because it's Vi, we say it's also normal basis. Yeah. Yeah. Yeah, this is the norm of Vi is 1, because it's an orthonormal. It's orthonormal, yeah. So now we see if you combine the left-hand side, right-hand side, you can see all the eigenvalues lambda I, they are non-negative. Yeah. Yeah. Okay. So now we know. Yeah. So yeah, it's Yeah, any question for this proof? Yeah, now let's talk about a definition of a singular values of a matrix. So it says if A is a m by n matrix, again don't have to be square matrix, then if lambda 1, lambda 2 up to lambda n, they are the eigenvalues of this. They are the eigenvalues of this, and 1 minute ago we just proved that the eigenvalues of this is non-negative, right? So we can safely define the root n. So we call the root of the eigenvalues of this A transpose times A, they are the singular values for A. Yeah, singular values of A is the eigenvalues of the A transpose times A. Yeah, right. It's a bit confusing here. The singular values of A is defined from the A transpose times A. Yeah, that's the definition. Yeah, and then here's the theorem. It says, let A be a m by n matrix with rank R, then A has precisely R positive singular values. So, which means the rank of A is R. Yeah, and then I know the number of positive singular values of A is also R, which means the positive eigenvalues for A transpose times A is also R, right? That's what this theorem says. So let's try to prove it. Yeah. So, yeah, hopefully everyone will remember what is a rank. If you don't remember, you can find this definition, like 4.6.2 in chapter 4 for the rank. Yeah. So let's say a rank R is the rank of A. Okay? Yeah. It's the rank of A. And then actually there's a theorem, I don't remember which theorem. It says the rank of A equal to a rank of A transpose times A. This is a theorem or lemma proving this in previous chapters. You can find this in the lecture note. Okay, so R is also the rank of A transpose times A. So now A transpose times A, of course, is an n by n. It's an m by m matrix. N by n matrix. It's an n by n matrix. Yeah. A is m by n. So A transpose A is n by n. Yeah. So the rank of A transpose A is equal to R, which means R is equal to n minus the dimension of the known space of it. Right. That's basically a definition. That's a rank. Yeah. The rank of matrix is of a square matrix. It's just the n minus dimension of the known space of that matrix. Yeah. Okay, so now, let's say, suppose this matrix A has precisely k positive singular values. Of course, later on we want to show k equal to R, but let's say suppose they have k positive singular values. So let is equal sigma 1, sigma 2, sigma 1. We can order them, of course. Sigma 1 bigger than sigma 2, sigma k positive. Then the non-zero eigenvalues of these A transpose A right? By definition of singular values, they are just sigma 1 square, sigma 2 square, sigma k square, right? Yeah. And then, yeah, so if we know this about we know the eigenvalues of this A transpose A, so now we can say the algebraic multiplicity of the zero eigenvalue for A transpose A is n minus k. If you don't remember the algebraic multiplicity, it is in definition. It is in definition. Chapter 6, 117, I guess, for the algebraic multiplicity. Yeah, because we know there are k non-zero or positive eigenvalues there, so which means for the zero eigenvalue, algebraic multiplicity is just n minus k, because the sum of them is like k. Yeah, and also by theorem, another theorem, 6.2.5, and this just says if a matrix is diagonalizable, then its algebraic multiplicity equal to a geometric multiplicity for each eigenvalue. So now we have the geometric multiplicity of lambda equals 0 eigenvalue for ATA is also n minus k. Yeah, and if we know the geometric multiplicity of a match of lambda equals 0 is n minus k, so we know the dimension of the known space of ATA is just n minus k. That's the dimension of the known space of that. So then we can just apply this to the first formula here. So now we know what is R. R is n minus k, which is k. Yeah. So we know this k is just equal to R. So the matrix A, has precisely, if the rank is R, it has precisely R positive singular values. Yeah. Okay, now let's find the singular value of this matrix as an example. So how to find the singular value of a matrix? So we need to find the eigenvalues of this. Find eigenvalues of this, and find the non-zero eigenvalues of this, and then we take the square root. We get the singular value of A. Yeah. So what's this? This is equal to 101, 110 times 101, 110, and by simple calculation, this is equal to 2. This is 1. This is 1, 2. Okay, it's a symmetric. Of course, it's a symmetric matrix. And to find the eigenvalues, this is just equal to the determinant of lambda minus 2 minus 1 minus 1 lambda minus 2, which is lambda minus 2 square minus 1, which is lambda minus 3 lambda plus minus 1. Yeah. So from here we can see the two eigenvalues are 3 and 1. Okay, so find the eigenvalues of A transpose times A. Yeah. And then what's the singular singular values are just the square root of them. Yeah, square root of 1, which is just 1. Okay, so I hopefully everyone knows how to find the singular value of a matrix, singular value of a matrix. Yeah, and as you can see here, these matrices don't have to be square. Right? Yeah. Oh, by the way, just to for that example, the two eigenvalues of A transpose times A is 1 and 3. We take the square root, but if you find the eigenvalues 0, you also take the square root of that. 0 also counts for the singular value of A. We don't like only take the positive singular value. 0 is also is also counted as a singular value. Yeah, but in this example, it's just what's it? Yeah, it's just 1. They are all positive, 1 and 3. So the singular values are √3 and 1. Yeah, all good. Yep. Maybe I only have time for a start of the definition of this singular value decomposition before we start with this singular values definition. Now, what's a singular value decomposition? It's called SVD. So if A is an m by n matrix, then the singular value decomposition SVD of A, it's a factorization of A by writing A like that. So A is a m by n matrix. So now we can factorize A as a product of 3 matrices, and where U and V, they are orthogonal. U is m by m, V is n by n, which makes sense, right? And sigma is diagonal, but it's not a diagonal square matrix, it's a diagonal m by n matrix. Yeah, for example, if sigma is have more columns, than rows, it's just like a non-zero value, or others are just 0. Yeah, this is not a square matrix, but it's also it's a diagonal m by n matrix. Yeah. So that's sigma. Yeah. So we can write. So if we have, so let's say, yeah. If we can write A as a product of these 3 matrices, like U and V are orthogonal matrix, and the sigma is diagonal. Sorry, I should say diagonal echelon matrix. Diagonal echelon matrix. Then it's basically the same. It's diagonal matrix. Yeah, diagonal matrix. Then we call this factorization is a SVD of A. It's a SVD. It's a singular value decomposition of A. So one question is just probably this is not unique. You can find maybe different, more than one singular value decomposition. That's also possible. But as long as this U sigma V satisfies this condition, we call that is the SVD of A. Yeah. And then here is a theorem about this SVD. Yeah. So let's say let A be a m by n matrix of rank or some rank R. Then if A is if you find a SVD like that, which means you find the U sigma and V. Okay. Now I can tell you these things. I can tell you, okay, for example, the non-zero entries of sigma is diagonal m by n matrix. They are just sigma I sigma I is from 1 to R is the rank of A. So this sigma I, they are non-zero singular values of A. Okay, before we know how to find the singular values of A, just non-zero singular values of A, they are the diagonal values of M. Yeah, and for like for V, the column, ith column of V is just the eigenvector of that with eigenvalue sigma square, sigma I square. Yeah. So if you tell me SVD, I can tell you all of these are true. Okay, I don't have time to go through this, but let's stop here. And on Thursday, I think Tim will continue from this SVD, and will tell you how to tell you the algorithm, how to find the SVD for a matrix. Okay, yeah.